A rotating detonation engine is often drawn as an annular combustor with a single wave racing around a ring. This paper looks past that simple wave motion to examine what happens after the detonation releases its energy, specifically how the channel shape dictates the internal flow physics. To test this, researchers experimentally studied two non-constant area RDE channels. This comparison moves away from the traditional constant area annulus to look at how linear, converging, and diverging shapes change internal acceleration. One test article was -3 degrees converging, with an area ratio of about 0.4. The other was +5 degrees diverging, with an area ratio of about 2.6. The team used 3 specific measurement streams to capture the behavior of these two channels. High-speed optical imaging through a transparent wall allowed them to observe the rotating wave and shock structures. Axial pressure measurements through a metal wall mapped the internal pressure distribution along the engine's length. Finally, thrust measurements recorded during operation quantified the performance differences between the two geometries. In the hydrogen-oxygen tests, the observed wave speeds ranged from 1690 to 1920 meters per second. These values represent roughly 55 to 67% of the estimated reference detonation speed. Because these waves are well below ideal limits, the experiment captures the non-ideal flow physics found in real engine operation, where channel shape becomes a critical variable. To understand the impact of the geometry, we first have to look at what stayed the same in both tests. Optical imaging showed that the strongest luminosity, marking the main heat release region, remained near the injector surface regardless of the channel angle. For the hydrogen-oxygen cases, the peak energy release occurred around Z equals 7 millimeters. The authors interpret this as evidence that the energy deposition location is governed primarily by the injector and the initial filling height in the setup. With the main heat release pinned near the injector, the remaining length of the channel acts as the primary volume for developing and accelerating the flow toward the exit. Let's examine the internal structure of the +5 degrees diverging channel. This map shows the diverging boundaries, with the heat release zone highlighted orange near the injector. Downstream of that zone, the high luminosity region identifies the oblique shock structure. In this expanding channel, that downstream structure is inclined backward relative to the wave's direction. This geometry allows the flow to accelerate rapidly and reach a critical point inside the engine, well before it reaches the end of the channel. This critical point forms roughly 23 to 27 millimeters from the injector surface. Under the author's quasi-one-dimensional interpretation of the exit velocity, the diverging channel reached an estimated exit Mach number of about 1.7 to 1.8. In this design, the heat release and the expanding geometry work together to drive the internal flow to supersonic speeds before it leaves the engine. The -3 degrees converging channel produces a completely different internal structure. The physical boundaries here narrow toward the exit, which alters the shock topology. Look at the orientation of the downstream shock structure in this geometry. Unlike the diverging case, this downstream structure is inclined forward relative to the detonation front. The converging walls force the internal pressure to build, keeping it higher throughout the combustor. This changes the acceleration mechanism. The physical area reduction provides the main mechanical acceleration, while the heat release primarily increases the pressure. This setup pushes the critical speed location all the way to the exhaust plane. In this specific experimental setup, the estimated exit Mach number was near unity. This converging geometry trades internal supersonic acceleration for higher internal pressure, with the flow only reaching critical speed as it exits the channel. Understanding these mechanics is vital for systems engineering. Downstream hardware, like a turbine, must survive the specific exhaust flow these geometries produce. This chart identifies channel geometry as an active design variable used to manipulate internal flow structure. The results show changing the angle alters shock orientation and internal pressure distribution. It also dictates the critical point location and estimated exit Mach number. However, there are strict guardrails to these findings. This experiment does not prove a finished RDE propulsion system. These results do not prove flight readiness, turbine integration, or a universal geometry that works for every engine. The measured performance in this paper does not guarantee total pressure gain performance across all RDE designs. The engineering takeaway is that the channel shape is a serious design lever that must be accounted for before an RDE can be connected to downstream hardware. By treating geometry as a variable, engineers can better predict and control how energy release translates into exhaust flow. For more engineering research breakdowns, visit www.proreadyengineer.com.